increasingly we're seeing that the worlds of machine learning and DevOps, data ops are colliding. So I won't steal Emil's punchline, but suffice to say that as Alex described, Seldon is engaging more and more with these types of foundational tech businesses. So I hope I've fluffed for enough time. Yeah? Emil,
thank you so much. Yeah, hello. My name is Emil Siemes. I'm with MESOS, solution engineer, working out of Germany. Today was planned to have Joel with me, who's based in London, but he has an incident, so it's just me today. My background, before joining MESOS roughly 2 years ago, I was with Hortonworks and SpringSource, and been involved in quite a few machine learning projects so far. Today, I really want to talk about building a data science pipeline and explain to you why we think that's necessary. And first of all, why is machine learning taking off? And we already get a good impression from Anthony because people want to do sentiment analysis or building self-driving cars or do fraud detection. So that's all understood, and we know, and we understand we need machine learning. But why data science platform? And the point here is, as a data scientist, what you really want to do is you want to write your awesome machine learning code. And well, yeah, I might be clean with a little bit of data, and then I train my model once, and then I throw it over the fence, and someone will operate the model for me, and problem solved. But actually, the real world is different. We're building you a nice little machine learning code, but before that you have to collect the data and clean the data, massage the data, verify the data, and it's a lot of activities you need to do. And then finally, when you got your model, you have to understand how you build up the serving infrastructure, you have to monitor it, you have to create a process to update it, and so on. So it's really a lot of complexity involved. And that's true if you're doing traditional machine learning. Why is everyone classifying dogs? I don't get that. But anyhow, so in traditional machine learning, you have your inputs, images, and then you have a data scientist doing the feature extraction, and then the classification, then dog or no dog. With deep learning, you're trying to get rid of this step and just throw a lot of data against the problem, and then finally get a model saying dog or no dog. But in both cases, whether it's deep learning process, so get the labeled data, a lot of pictures where you know it's a dog, then you train your model and you have the output model, and then the next step really is with the trained model, you apply the model to new data, new image. And then you get the classification. And it's very similar with traditional machine learning. And as Anthony also mentioned, when we are looking at the neural networks, then in the beginning you have networks who are really detecting very simple things like lines or dots or something. And then the layers above are using this information to detect, eyes or noses, and then the final layer detects or classifies whether there's a dog or not. And initially, this looks pretty straightforward. So the data scientist sits at his notebook, uses TensorFlow, makes his model, and then the problem is how to get that into production. And here is some experience from a consultant at Google who said, well, it's really a hard problem to operationalize these models. Many companies are failing with that. And as we just learned, Kubeflow was introduced to solve some of these problems, right? You got your Jupyter notebooks, you train your model, you monitor it, and you debug it, and you serve your model. But reality is that even Kubeflow alone is not good enough. because as we learned from the slide before, you need all this labeled data, and you might clean it, massage it, and what have you. Normally that's done with Spark, so you might need Spark, and you need storage, whether it's on cloud or Amazon S3 or whatever. And you might have streaming incoming requests, which you want to evaluate with your model. So in a public cloud, this with Kubeflow seems to work really nice because you have all these distributed services already prepared for you by the cloud vendor. But things are looking a little bit different when you are running your Kubeflow on-premise in your own data center, right? Because then it's your responsibility or your operator's responsibility to provide Spark as Kafka for streaming, or HDFS as a distributed file system, or Spark for doing the data transformation. This is really what DCUS tries to provide or give you as the data scientist. So it's a platform which helps you in all these different steps, from data streaming, with HDFS and Kafka, the model engineering side, whether you're doing that with Zeppelin or Jupyter notebooks, the training with TensorFlow or PyTorch or what have you, and then the model management and the model serving. And we are going into each of these. So if you start with from left to right, data streaming, that's really mostly done nowadays with HDFS or Apache Kafka or Cassandra. So there are multiple options for you, and we're addressing them all. So you would store your labeled data in HDFS, as an example, and then you can really store tremendous amounts of data. Data preparation nowadays is mostly done with Spark and Flink. We don't see MapReduce too much anymore for that, but these two are really the most used tools for that. In the on the model engineering side, we see mostly Jupyter notebooks, but Zeppelin as well. So these are the web-based front ends for data scientists to write their code, whether it's in Spark, ML, or what have you. And as an operator, of course, you have multiple users to serve. So some want Zeppelin, others want Jupyter notebooks, different teams, different organizations, and you have to think about how do I present each of the teams with the tools they really want and need. And then training the model. Again, TensorFlow and the notebook, that looks pretty easy. But when you get into a distributed TensorFlow situation, then it's getting more tricky, right? You have to prepare the machines, you have to install TensorFlow, you have to wire these things together, you have to provide your code to run on every machine. And the more machines you have, the harder this gets. And it might not only be TensorFlow which runs on these machines, right? Different teams, you have, some are using maybe PyTorch, who is going to get the graphic card, right? Who is going to get all the power, the CPUs, the memory, which teams? And this is actually what the background, or where Apache MESOS is coming from. So Apache MESOS is an open source project which started at the University of California, Berkeley, within the AMP labs, exactly where Spark was coming from. And Spark was actually initially one of the test frameworks for MESOS. That's the icon of MESOS. And the idea behind MESOS is that you break up the silos you have in traditional data centers, where you've got a bunch of machines for Kafka or Jenkins or TensorFlow or Spark. But you're breaking these silos up and then have on way less machines the same workloads running on the same machines. So you're getting a higher utilization on your cluster. And that's actually what DCUS does. So DCUS has MESOS as its kernel, and then run Kubernetes and TensorFlow and Spark and hundreds of different workloads on the system to help the data scientists, but also traditional applications on any infrastructure. So whether that's in cloud, virtual machines, or physical infrastructure. And the idea behind it was really to help the pure operator to wake up in 3 a.m. in the morning when he had one problem with all, one of these services. It was born within Twitter and Airbnb, where our founders were operators and had this nightmare. The telephone was going on in the middle of the night, and they just wanted to get rid of all that. So they invented MESOS. And the idea here is really, you got a system of master machines, and you get on the machines within your cluster where your workload runs, agents running, which are collecting information, how many CPUs are available, how many graphic cards are available, which ports open, which storage you have, and so on. Sending the data back to the MESOS masters, which are a zookeeper ensemble, and then providing these resources to the schedulers. And the schedulers are then specific for each workload. So you got this scheduler for Kubernetes, a scheduler for TensorFlow, for Spark, for HDFS, and all the knowledge how to operate this individual workload is built into the scheduler. So the scheduler does not only understand how many resources a certain workload needs, it also understands how to update the workload, how to make it secure, how to scale it, what to do if it fails, and so on. And that was really the background of Apache MESOS. It was, or is the only scheduler with this two-level scheduling, as I mentioned. One very simple, just collecting information about the available resources. And then the second level scheduling, which is workload dependent and therefore understands the application and the needs of the application. And then getting back into the model management. When you are creating these many models, and the more models you have, the better it is, and you might have competing models, trying out different algorithms, different data sets, and so on. Then again, you have to store these models, right? Again, you might store them in HDFS or Cassandra or any other database. And then finally, you want to serve your model. And as we learned, there are multiple options available as well. That might be Seldon core or TensorFlow serving. And you also might want to do, canary deployments where only on a subset of incoming information you want to apply a specific model and another model on other incoming data. Or you even have a rendezvous architecture where you run different models in parallel and then either average things or you look at the common outputs on certain models. So you get your input and evaluate different models, and then have your scoring, and then you get your response back. And furthermore, it's also about monitoring and operations. It's probably the most boring part. But if you really want to run models in production, of course you have to care about monitoring and operations as well. How to scale, how to upgrade, how to patch, and all these things. Just a couple of links here. Most stuff is on GitHub. ThisUS itself, it's available as open source, as an enterprise version. And I don't know how many minutes do we have left? 5 minutes? Okay, that's good. Because I also want to give you a quick demo. So this is the dashboard of ThisUS. It gives you some information about the allocated CPUs and memory. That's similar like a task manager on Windows, but this is not for a single machine. this is cross my cluster. So I can have a look at the nodes, and we will see that altogether there are 70 nodes. Right now they're just in one availability zone in Amazon, but that, as I said, that could be also on-prem or distributed over multiple regions or zones. And I can go to the grid mode, and we can see that how MESOS distributes the different workloads on these machines. As I said, that was really the idea behind MESOS, breaking up these silos and run different workloads on the same nodes. And you see that by color. Zeppelin, okay, this machine is completely used by Zeppelin, but this one here has multiple colors, so there's something running from Cassandra and Kubernetes, Marathon. And I got a couple of services deployed here. Kubernetes we already saw, Zeppelin is running here. We got development tools like Jenkins and GitLab. What else do I have? I got my data services, Cassandra, Elastic, Kafka, Kibana running here. And by the way, the application, just a simple hello world of machine learning, if you will. So I'm simulating heart rates from users. And in Zeppelin, I did a supervised model, just a linear regression, very simple. And then the output here, that's really clumsy, I'm getting PMML as a result, and then taking the PMML, which is my model, put that into Zookeeper and evaluate that when new heart rates are coming in. These are the data services used. Yeah, something which is quite neat in DCUS is the catalog. Like an app store where you pick the services you want to run on your cluster. Like if you would want to run TensorFlow job, you would just say, okay. You give it a name. You specify if you have it categorized where KDC is running. Then you provide it with a job URL, a job name, provide how many parameter servers you want to run, how many workers you have, how many GPUs this job should get, and so on. And then you would just review and run that. And very simple, a simulant with all the other services like whether you want to run Spark in the cluster, Kafka. You would just go to the catalog, tell the system how big and how strong the Kafka service should be, how many CPUs in memory, and then within a minute the service is deployed. But as I mentioned, it's not only the deployment, it's also the operating it, making sure all the tasks are up, how to upgrade, how to patch, how to scale out, and so on. All right, so that was a very, very quick introduction into DCUS and building data science pipelines with DCUS. You got any questions?
Do you also support KDE
KDE?
as a data source? So instead of HDFS, for example.
Not that I'm aware of.
It's fine.
Yeah. How does it compare to HDFS?
Well, it's a different concept. I mean, HDFS is kind of built for distributed systems. KDE, not necessarily can be signal only and is kind of just a NoSQL database.
Okay. Yeah. I haven't managed the field so far.
Okay.
Yes, please.
So in the data preprocessing pipeline that is I guess the second part.
Yeah.
You mentioned Spark and I think one other thing, but you left out something like Luigi or Airflow or like the other ETL orchestrator. So is there a reason for that? Do you not see people using that too much, or is there like? I was just wondering.
Yeah, I would say
we were looking
90% of the customers I'm talking to either using Spark or Flink.
Okay.
Airflow I met sometimes,
Okay.
but that's actually it.
And then do you think there's a reason for that particular? Because I understand that, like, to me, Spark sits in a very different cluster from like Airflow for what I would use it for. So I'm just wondering, why do you think Airflow maybe doesn't have, even though it's like supported by like lots of open source contributors and so on? You know?
Well, I mean, from our perspective, we prefer to build a system where every workload can run together with all the others, and they're not getting into their way. And most of the customers are struggling with getting expertise from the market. And this is why I think we see mostly Spark, because there's just the most knowledge. Is it the best tool? Probably, maybe not. I have a question here, maybe. Yes, please.
So I have one question. So I don't know the product that you described in practice, but I have recently saw a presentation for container orchestration product called OpenShift from Red Hat.
Yeah.
And I'm just wondering if this two product would be comparable in some way.
It is. We are somehow competing with it. That's true. So OpenShift is a modified Kubernetes offering. So it's mostly good for running stateless applications, like web stuff or so. Where we are differentiating is that we do run stateless stuff in Kubernetes or in Marathon in a container orchestration, side by side with the data services like HDFS and Cassandra and so on. Does that make sense?
To some degree, because the way I understand, if you want to run Cassandra, so Cassandra needs data nodes where you're going to store data.
Yeah.
So lots of terabytes of
Yep.
data on a disk you need. And then you need some nodes who's going to do the orchestration, operation, distribution, application, that kind of stuff. So if you run this, let's call it the control plane in containers on Kubernetes, on MESOS, or OpenShift, it doesn't really matter, to my understanding.
Well, you don't run the data services in Kubernetes. In production. In development you do, but in production you don't. Because Kubernetes is a single level scheduler. So from a Kubernetes perspective, each container is just a container and has no idea what's running in the container, right? But in a distributed system, if you do an upgrade or a patch, you have to understand what the requirements are. First, I need to upgrade these sets of containers, and then I need to, one after another, upgrade the others, or register a new one. And this knowledge you can still, you can have sidecar pods in Kubernetes and build that all in, but it comes out of the box in DCOS on MESOS.
Right, I have some clarity probably for the more reading. Thank you.
Okay, welcome.
Very good. Do we have any other questions? No? In which case, it leaves me to say thank you, everyone.